I'm Ben Turner, and I'm going to be speaking about private identity agreement for private set functionalities. I did this work with Ben Corridor and Sarfar Patel while I was an intern at Google and while I was a student at UC Santa Barbara. First, let's talk about private set functionalities. Private set functionalities have gained a lot of attention over the last few years as real-world applications of multi-party computation, including as an example for aggregate ad attribution. We consider a scenario in which two parties, Alice and Bob, each have a database that contains sensitive information. They would like to evaluate queries on the join of the two databases without leaking either party's sensitive information. In the idealized version, Alice and Bob both send their databases to a trusted party, and then Alice and Bob can ask multiple queries of the trusted party, which responds without revealing any information that is not relevant to the queries. In practice, protocols for private set functionalities require two logical components. In the first, parties perform some private set intersection to identify the rows in their databases that correspond to the same user, which they've identified with some unique primary key. In the second, the parties perform some aggregation on the data associated with those rows. So, for example, Alice and Bob could ask, how many unique rows are there in the intersection of our two databases? Or, taking one small step forward, they could ask to compute the sum over a few columns in the intersecting rows. Importantly, the previous technique depends on the existence of primary keys that are somehow shared by the two databases. This allows the two databases to claim that their data come from the same universal set when invoking a PSI. The essential question of this work is how to agree on those primary keys. Ideally, we'd like the keys to be reusable so that we only have to construct new keys when the data change. This question is very similar to concurrent work by a group at Facebook, although ours includes an additional twist that makes our problem more difficult than the one they consider, but they achieve much faster performance than our prototype. In the new paradigm, we envisioned that an ID agreement protocol would be used as a setup protocol for PSI or some PSI with aggregate statistics. First, the parties would invoke the ID agreement protocol to agree on a set of primary keys for the rows in their databases. And they would then use the new primary keys as inputs to a protocol that computes PSI or PSI with aggregate statistics. Our goal is to allow the parties to invoke PSI protocols many times without needing to rerun the ID agreement protocol. In this example, we'll consider a situation in which Alice and Bob's databases have some data in common. And our goal is to assign primary keys, which is the ID field in this slide, to the records of the two databases. Our intuition is that both Alice and Bob have some identifying information about their users, and they can use this identifying information in order to construct some abstract notion of an identity. They can then match identities over information that they have in common. For example, an ID agreement could assign Alice's second row and Bob's first row the same ID because the corresponding row in each database has the same phone number. Our rule is to assign two rows the same primary key if any of the columns have the same data. In this situation, it doesn't matter to us that primary key 3 has a different name in Alice's database than in Bob's database. And if either database contains a row that does not match with a row in the other party's database, the assigned primary key must be unique among all the primary keys that are issued. Looking ahead, we point out now that any ID agreement protocol must output either encryptions or shares of the primary keys that are assigned to the two databases, and then the subsequent PSI protocol must be modified to take the encryptions or shares of primary keys as input. I'll explain later why this is necessary for privacy, but first we're going to take a quick detour. Our detour is to propose a new abstract problem for multi-party computation called two-party component labeling. We'll then show how to use this problem to solve identity agreement. Imagine there is some big graph in the sky called G, and G is special because it is a forest composed of many small connected components. And let Alice and Bob each have some local graph that is a subgraph of G. We note that every vertex in G must be uniquely identified. In this picture, we've colored G to indicate the vertices in both parties' local graphs as purple. Vertices in Alice's graph only are blue, and vertices in Bob's graph only are red. In the two-party component labeling problem, Alice and Bob must assign labels to the components in their local views that reflect their components in G. First, they will do their best to reconstruct G using their local subgraphs, and then they can uniquely label the components in the graph that they construct. And each party can output a component label for each component in its local graph. Now, we can easily reduce secure identity agreement to secure component labeling. The idea is that each party can convert its local database to a small graph, which is composed of many connected components. Each piece of identifying information in a database is mapped to a single vertex in the graph. And there must be a path between every two vertices in the graph that represent the same abstract identity. Now, we can imagine that the graph G in the sky represents a universe of distinct identities and their identifying information. Each component in G corresponds to a single identity in the real world. In the reduction, the unique component labels that are output from component labeling can be trivially used as unique representations of an abstract identity, or, for example, a primary key. Now that we have a nice abstraction to think about the problem, we can return to our earlier point about why ID agreement must output encryptions or shares of primary keys, and not the keys themselves. Recall that in our earlier example, Alice and Bob do their best to reconstruct the graph in the sky, G. But if you look at only Alice's view, it becomes clear that two separate components in Alice's local graph are in the same component in G. It must be the case that Bob's graph had some component that shared a vertex with each of these two separate components in Alice's graph. If Alice learns the component labels of these two components in her graph, then she learns important information about Bob's graph. In the reduction, if Alice learns that her two components are assigned the same label, then this means that Bob had some identifying information that would allow Alice to combine two separate rows, or identities, in her database into a single row. But this is a very serious violation of privacy. In the idealized version, the trusted party would never leak information about the intersection of the two databases, which the parties could not infer from the outputs of their queries and their own inputs. The fact that one party can connect two rows in the other party's database must not be revealed. It's for this reason that we require any ID agreement protocol to output an encryption or a share of every label, and not the label itself. And then, any composed PSI protocol must be modified to take the encryptions or shares of the primary keys as input. We also note that this is the difference between our formalization of the problem and the concurrent work by the group at Facebook. They make an implicit assumption that the process of computing unique identifiers cannot suffer from the fact that some party may connect two rows in the other party's database. Intuitively, they must assume that each row in Alice's and Bob's respective databases already represent a unique user within the database. We do not assume such uniqueness, and it is this data cleaning issue that makes our solution so much less efficient. In the rest of this talk, I'm going to present an algorithm that we use in order to compute identity agreement, and then a protocol that we use to securely implement the algorithm. The algorithm is called Percolate-and-Match because those are the main steps of the algorithm. First, recall that each party has an input graph, which is guaranteed to be a subgraph of some big graph in the sky. And also recall that each vertex in the big graph in the sky can be uniquely identified. As a setup step, each party will annotate each vertex in its local graph with that unique identifier. Using the same example from earlier, we can let each unique vertex be represented by a unique letter. If both parties share a vertex, then the vertex must be labeled with the same letter in both graphs. As setup, each party will make a note of the vertex's initial identity. We will let the vertex's true identity be annotated to the side of the vertex, and we will start to modify the label of each vertex that we put inside the vertex. In the first step, each party performs a percolation among the vertices in its own local graph. This means that each party looks at the vertices in its own graph and assigns to each distinct component in its graph the minimum label among all vertices in that component. As an example, we can look at the component in Alice's graph that contains vertices A, B, and C, and we can expect that at the end of a percolation step, all of the vertices in that component will have label A. You can see that after a percolation step, every vertex in a distinct component in either party's local graph has been updated to have the same label. In the next step, called the matching step, the two parties compare and update the labels of the vertices that are in the intersection of the two graphs. In this diagram, we connect Alice's and Bob's graphs via dotted lines, where on each side of the dotted line is a vertex that is in the intersection of the two graphs. In a matching step, Alice and Bob compare the labels that have been assigned to the vertices in the intersection. For each vertex in the intersection, the parties update their individual labels for the vertex to the minimum of the two labels it was assigned before the step. In this example, we highlight with a blue border every time a vertex label is updated in Bob's graph based on a label that Alex had given the vertex, and we highlight with a red border every time a vertex label is updated in Alice's graph based on a label that Bob had given the vertex. The percolate-and-match algorithm simply requires that Alex and Bob repeat percolation and matching steps until all the vertex labels have stabilized, which means every vertex has achieved the minimum label that is possible for it. Continuing with the example, Alice and Bob percolate once more. We see that after one more percolation, Bob's graph has already stabilized, but there is a component in Alice's graph that still needs to be updated. It is one of the two components in Alice's graph that must be connected by a component in Bob's graph. So we continue to match again, and Bob again updates a label in Alice's graph, after which Alice percolates one more time, and now all of the vertices in both graphs have stabilized. Looking at the joint graphs, we see the original labels that were assigned. And we can fast forward to the final labels that are assigned to each vertex. We can trivially label each distinct component in the graph with the label of any vertex in that component. Because all such labels are the same, this label uniquely identifies the component. We still have to answer the question of how many times one must iterate the percolate-and-match algorithm. The pathological case looks like this. Solid lines represent edges within each party's local view, and dotted lines again represent vertices that are in both parties' views. Neither Alice nor Bob has done a very good job of connecting the vertices in its local graph. We have a lemma that if the maximum size of a component is m, then percolate-and-match stabilizes in at most m-1 iterations. In the secure implementation of this algorithm, the two parties must somehow figure out an upper bound of m beforehand and provide it as input to the protocol. We consider this to be a reasonable assumption. We designed a garbled circuit protocol that allows us to securely implement percolate-and-match. We'll now show how we achieved a circuit that is reasonable for some real-world size problems. We will describe the protocol using a flow diagram, and at each step, describe the gadget computed by a garbled circuit. First, the parties label their vertices as in the setup phase of the perk-and-match algorithm we described earlier. However, in this protocol, we assume a random oracle that we implement as a hash function, and hash all of the vertex labels to some uniform length. This alleviates problems that arise from identifying information coming from a universe with varying lengths. The output length of this function is a tunable parameter, and it is set in order to avoid spurious collisions. After labeling their vertices, each party locally sorts its vertices and submits the ordered list to a garbled circuit as input. After receiving the inputs, the garbled circuit merges the two sorted lists. Using a batcher merge, which is the first step of Batcher's sorting network, this can be done in n-log-n comparisons. Note that in the merged form, any vertex that is shared by the two parties must occupy consecutive indices in the list. This will be important later on. Then the circuit randomly permutes the merged list. Each party submits randomly generated select bits, and the circuit uses a Waxman network to permute. We do this in n-log-n comparisons as well. In the next step, the circuit walks through the permuted list and outputs each vertex back to the party that contributed it to the circuit. This can be done easily by including a single extra bit with each vertex to describe which party contributed the vertex. Each party now knows the location of each of its vertices in the randomly permuted list, but it does not know how the other party's vertices have been permuted. In the proof, we have to show that as long as either party is honest, revealing component indices does not reveal any information, even though the location of components could be considered intermediate values. Each party uses the locations of its own vertices in order to determine the indices corresponding to each component in its local graph. The parties reveal to each other the indices corresponding to each component in their local graphs, and then use this known information to hardwire subcircuits that perform percolation for every one of both parties' local components. To percolate within a single component, we simply need to compute the minimum element of a small number of vertex labels, and then update every vertex in the hard-coded component using the minimum label. Next, the parties invert the Waxman network in order to return the initial form of the merged list. The circuit then walks through the list again and checks every pair of consecutive indices to determine if they contain the same vertex. The circuit performs an oblivious update of each label that assigns the min label to both slots if the two slots represent the same vertex. Note that this part of the circuit, in particular the matching phase, is very similar to a technique used by Wong, Evans, and Katz in 2012 to perform private set intersection using garbled circuits. The circuit then simply iterates the Percolate-and-Match procedure m-1 times, permuting or inverse permuting at each step to go between percolation and matching stages. The circuit ends with a final matching stage. After the final match, the circuit outputs masked versions of each party's vertex labels to the other party. The circuit uses one-time pads, which are provided by each party as input, to mask each vertex label before outputting it to the other party. In the paper, we also show that we can use any CPA secure encryption scheme with XOR homomorphism to output encryptions of vertex labels under a key known only to the other party. This also costs a few extra rounds. In this picture, you can see a full version of the pipeline diagram, from the input stage to the output stage at the end. We also wrote a prototype implementation using obliv-C, and modified obliv-C in order to improve the performance by about 50%, and we ran it on Google Compute Platform over LAN. We think that if we use stacked garbling, we could probably design a better circuit for this. We ran the implementation for inputs at various sizes of 2, at various powers of 2. Note that the security parameter in this diagram represents the probability of spurious collisions for the hashing in the setup phase, and does not reflect the length of the garbling keys. You could consider that this security parameter tunes correctness but not privacy. We also chose m=4 for our implementation, and in the paper you can see that we also benchmarked how long it took to perform just Percolate-and-Match, so that you can extrapolate for larger values of m. The previous graph looks exponential because the input sizes we used grew exponentially, but you can see that if we plot the x-axis linearly, then the runtime looks more like n-log-n as we expected. And now we can open it up to questions.